Hello everyone, we are Team Triksham from the Anand Saga University. We are a team of 12 students from different departments. We have been working on our project for last 5 months. We would like to introduce to our board Makardhwaj for IRC 2025.
Our modular rover is designed for versatility and durability with each component engineered to easy assembly and adaptability. A lightweight aluminum chassis and broker bogie suspension ensures the stability on rugged terrain, while precision manufactured parts related to additive manufacturing and laser cutting allow for the seamless interchangeability. Using advanced assembly tools, we have achieved the refined finish that aligns each modular piece perfectly. This adaptable design is mission ready, suited for diverse challenging conditions.
Our rover is equipped with a robust control system featuring both microcomputer and microcontroller, where microcomputer manages all the autonomous part and generating a command that it communicates with the microcontroller. Each motor is powered by individual driver and power supply, where it ensures that the rover will return to the base station even if one motor driver fails to move. We even implemented the differential power supply system wherein locomotion is powered, arm and ABX will be disconnected from the power to conserve energy.
The overall control of our motor is achieved by a hierarchical master and slave network communication between a microcomputer and a microcontroller. So the microcomputer works as a master, managing all the high-level commands, and the microcontroller works as a slave, managing all the detailed control of the motors. This whole setup ensures our efficient power distribution and seamless communication between the components.
Image recognition techniques that we have implemented in order to detect the direction of the arrow. For that, we have used OpenCV, which actually converts the image of the arrow to grayscale, and based on the degree at which it is inclined from horizontal plane, we are going to decide in which direction the rover should steer.
We have developed an in-house 6-degree of freedom robotic arm with a fully 3D printed cycloidal gearbox, which gives us a gear ratio of 20:1 and a torque of 15 kg per meter. It has 2 linear actuators for the forward and backward mechanism and a 3D printed gripper with a bevel gear system for the rotation and a stepper motor for the opening and closing.
Our rover consists of a configurable monitoring system which mainly focuses on camera monitoring while prioritizing battery conservation. With n number of cameras connected to the rover, any number of camera can be turned on while others will be in off state. This flexibility allows rover's resources to be used for further experiments.
Our ABX ground sample collection model consists of 3 independent linear actuation systems, which gives us the accessibility of 15 cm depth to drill. We have 2 different kinds of drill bits. One is an auger bit, another is an acrylic bit, so which gives us for stratigraphic profile. So we have another module which to test upon the soil NPK sensor and also a microscopic camera.
The soil that comes out from the auger bit is moved to the beaker, and in the beaker we will be transferring the solutions A and B for mixing them with the soil. After the process is done, after the mixing is done, the mixed liquid is then drawn out with the help of a pump and transferred to the test tubes for color analysis. And based on the color analysis, we shall be measuring the concentration of carbon. And for measuring the environmental factors and the composition of the soil, we have an NPK sensor here which will help us in determining the nitrogen, phosphorus and potassium content along with the humidity, electrical conductivity and pH of the soil.
We have developed a sophisticated intra-rover communication system. A dual-stack parallel master-slave model has been implemented where a microcomputer acts as the commandant and a microcontroller as a slave. The relevant feature helps us to advance the command program and elevate the features again for the purpose of diversity. We use Robot Operating System OS version 2 as a framework for integrating all modules and events performed by the roving system. ROS TCP networking protocol is being used for the inter-rover communication to the base station.
Our terrain mapping system consists of inter-realisance G435 camera along with RTAP map algorithm. This setup allows us for real-time 3D mapping by merging depth and color data. We have generated grayscale map and we have successfully retrieved reconnaissance along with the path traversed by the rover.
Our rover features 2.4 GHz deep-link antenna facilitating reliable data communication over a line-of-sight range of 500 meters. The onboard sensors are meticulously managed and controlled by microcontroller computer hierarchical network, ensuring reliable data acquisition, processing and transfer.
As per the requirements of the competition, we have a very easily identifiable and accessible kill switch. Pressing this kill switch will kill any kind of power to the motors.